Why don't we get started? So there is project due, simple web server. If you are using Python 3, please indicate you're using Python 3, and at least on the Unix command line at the beginning of your uh, Python program, if you type $ um, user bin Python 3. What that does at the beginning of your Python program, it allows you to run it from the command line, and it will cause the right version of Python to run, namely Python 3. So, yes. Oh, is there? Yeah. Okay. Exclamation point too. All right. $, uh, exclamation point, is that it? All right. Okay. Yeah. So typo. Thank you. Um, so if you're using, I used Python 2.7, but you can use Python 3, Python 2.7. I guess as of February, they're no longer updating it. So if you use Python 3, that's fine. It's up to you. You can search enough online sources to find the APIs. The socket APIs shouldn't have changed between 2 and 3, but you're certainly uh, uh, welcome to use Python 3 and not Python 2, but please indicate the version of Python you're using, and it would be immensely helpful if you include that run spec at the beginning of your Python program. Um, the website zip file, please include the website content, and your Python server program will be inside of that folder that contains the website content. And I will be running that web server and testing it with my browser. For the host name, if you're going to use a host name that's different from the so-called loopback address, the loopback address has the following IP: 127.0.0.1. Please make sure if you test your server on a different host from your own machine, that's fine, but make sure to change it when you submit it so that you're using the loopback address. I don't want to, and I won't, go in and edit 18 programs in order to grade it. So please make sure it runs out of the box using loopback address. Any questions? So it's due on Thursday at the usual 1 second before midnight, and we won't have any work assigned over spring break. It's for you to enjoy, not too much, but to enjoy nonetheless, and make sure you don't catch anything and bring it back to campus. All right. There is a coronavirus going around. It's a real thing. So please do be safe and exercise good precautions. But nonetheless, so homework is due on Thursday. So where we last left off, we talked about the utilization of a gigabit link is very limited based on the protocol. And it was due to this stop and wait behavior that the reliable data transport had engaged in. It sent a packet and then waited for the ACK to come back. And during that round trip time, that RTT, it didn't send anything else. And so effectively, that channel was idle throughout that time. And in order to better the utilization, rather than being idle, waiting for the data packet to go across and the ACK to come back, why not send more than one packet during that time? And that's exactly what so-called pipelining does. And so in order to do that, the pipelining, the sender allows multiple in-flight packets. Now, in-flight means that it has been transmitted, but it has not yet been acknowledged. So the feedback from the receiver has not yet arrived back to the sender. And so in order to have multiple in-flight packets, rather than alternating between packet 0, packet 1, packet 0, packet 1, you're going to have a range of sequence numbers maintained by the sender. And then you're also going to acknowledge those sequence numbers at the receiver. And so this idea of increasing utilization by having a set of packets and a range of sequence numbers, and these packets can be unacknowledged, i.e. in flight, it's called pipelining. And so in the figure on the left here, we have stop and wait. So you send your data packet in the forward direction from sender to receiver. Nothing else happens. No other data is sent. And then you get back this green path and the return path from the receiver back to the sender in the form of feedback, which is the acknowledgement. And in pipelining, this second figure on the right, you have the data packets going in the forward direction from the sender to receiver. And we have some window of data packets. That window can be different sizes. It doesn't matter what the size is, but it's n many packets that can be in flight, i.e. unacknowledged. And so we have your n many data packets that go across the wire in the forward direction from the sender to receiver. And then we have the acknowledgements coming back on the reverse path is feedback from the receiver back to the sender. Okay, so there are two major flavors, if you will, of pipelining. One is called go back in, and the other is called selective repeat. Okay, so let's continue on. And so the reason why pipelining works, or pipelining is a thing, is because it increases the utilization of your channel. In the case of stop and wait, we transmit one packet and then we wait round trip time plus the transmission time for that packet to be sent and then for us to get back an acknowledgement. But during that time, when it's in flight, before we get the ACK in this region, RTT of time, from the sender's perspective, we're not utilizing that channel. And so when you pipeline, you're sending multiple packets back to back to back, one after the other, from the sender. In this particular case, we send 3 packets. The first packet is this first sliver here from time t0 to time t equals L over R. So L is the packet size in bits. R is the transmission rate in bits per second. And so you'll notice here in time increases going down the board. On the sender side, at time t equals L over R, we've finished transmitting that last bit, as it were, of that first packet. Now, during that time between L over R, that RTT, right, that RTT seconds later, we have time t equals RTT plus L over R. Now, during that time, in this particular example, we send 2 more packets. So we start immediately right at t equals L over R. We start transmitting a second packet at another L over R time, and then a third packet, another L over R many seconds. And so now we have 3 packets in flight at this point here, which just consequently happens to be 3 times L over R. We have 3 packets in flight, meaning 3 packets have been transmitted. They're down the wire somewhere along the pathway between sender and receiver endpoints, but they have not yet been acknowledged. Any questions about this? No? Make sense? All right, so let's see what happens. So now at time t equals RTT plus L over R, we get the acknowledgement for the first packet, and then we get the response, and then we get the acknowledgement for the second packet, and then the third packet. So that means during this time, RTT plus L over R, now we're sending 3 times as much data, right? And so the time spent actually transmitting data is 3 times L over R because it takes L over R seconds to transmit data. And so this utilization talks about the proportion of the time that is spent actually transmitting data versus just sitting idle. And so from before, our calculation had in the numerator 0.0008, and now our calculation, if we take the amount of time being spent sending data, it's 3 times what it was before, 3L over R in the numerator, and in the denominator we had as before, RTT plus L over R, which is the time that includes the transmission of the first packet up to when we start getting acknowledgements. And so you do that calculation, you've now tripled the utilization rate. And so if you increase the number of packets in flight beyond 3, you're going to increase the utilization of your channel. Okay. Any questions about this? Does that make sense? Okay. And so the whole reason for pipelining, whether it's go back in or selective repeat, is to increase utilization. Okay. And so let's take a look at the behavior between the two. Now, of course, many times in systems like computer networking, operating systems, but in this case, this is one of those examples where it's not a matter of which one is better. It depends on the application, what you're after. And so selective repeat and go back in are two approaches for pipelining, i.e. having a window of packets that can be in flight, i.e. On their way to the destination and not yet acknowledged. So let's take a look at go back in. So the sender can have up to n unacknowledged packets in the pipeline. So the n is the window size and n is the number of packets. And the receiver only sends so-called cumulative acknowledgements. What does that mean? So let's say if you have a bunch of sequence numbers, sequence number 0, 1, 2, 3, 4, if you get an ACK of 2, that means that ACK of 2 means that not only has packet number 2 been successfully received, it means packet number 0 and 1 have also been successfully received. So in go back n, acknowledgements are so-called cumulative in the ACK number. Okay. If there's a gap in the packets that have been acknowledged, it only acknowledges that sequence number cumulatively up to where that gap is. So it has to be contiguous. There can be no gaps in terms of sequence numbers for packets that have been acknowledged. So in the case of saying sequence number 0, 1, 2, 3, 4, right? If packets 0, 1, and 2 have been received, and then 4, 5 have been received, that cumulative ACK is only going to ACK up to 0, 1, and 2, right? It does not cumulative ACK if there's a gap in sequence numbers for the packets that have been acknowledged. And so the sender has a timer, and recall, a timer is used to determine whether or not there was congestion, i.e. has it taken too long to receive an acknowledgement. And so the timer is associated with the oldest unacked packet. That means the smallest sequence number, right? And when that timer fires, it doesn't send just that packet, it sends the entire window's worth of in-flight packets. Okay? All right, any questions about this? So that's go back in behavior. And the converse for that, the other form of pipelining, is called selective repeat. Now, with selective repeat, it's a little bit different. Selective repeat is called selective because every single packet in this window of n many packets that can be in flight, every single packet has its own timer, right? So what does that mean? What it means is that if a packet has taken too long to get to the destination, only that packet is resent because it's on a per packet basis. These timers are defined. So if you have a window of size n, that means you're going to have n timers, one for each packet. Now, in the case of selective repeat, well, when you do a resend, you only send that particular packet, which is missing, that has not been acknowledged, right? Instead of sending the entire window. Now, of course, you might wonder, why would I do one versus the other? Well, in the case of selective repeat, and this is the cost you pay, selective repeat, you have n many timers. So you're using more timer resources in your operating system runtime, right? You only have a finite number. But the benefit is if you're going to resend, you're only going to resend individual packets. Now, when you're resending data, that contributes to the amount of traffic on the wire, and that amount of traffic on the wire contributes to congestion at the routers. So that means it only resends exactly the amount of data that it needs to on an individual packet basis. Now, go back in, it sends the entire window's worth, okay, but it only uses a single timer, right? So it uses fewer timer resources from the OS runtime. And the other thing, the flip side for go back in, is that if just one packet from that window of n many packets that are in flight, if just one packet is unacknowledged, it resends the entire n packets, right? Now, for some applications, it can be beneficial because if you start getting congestion, congestion increases, and then something breaks, and then it decreases. And so conceivably, if you're going to get congestion, you're going to get congestion impacting subsequent packets that are nearby one another, meaning you send the first one, you send 10 packets, you might get congestion associated with packets 0 through 3, and then the other remaining ones don't have congestion associated with them, right? Block structured data. Okay. Any questions about this? And so the important thing with selective repeat versus go back in, it's not a which one is better, it's what is the conditions you have, And is it important to spend more resources on the OS runtime for more timers to save on how much extra traffic you're pushing through the wire due to resets, right? And they both have their drawbacks and their benefits, but it really is application dependent. Okay. Any questions about this? Does that make sense? Okay. So let's take a look at the sender window behavior for the go backend pipeline protocol. And so the sequence number in stop and wait was just alternating between 0 and 1. And here we're going to have a k-bit sequence number. And so the sequence number, if it's 8 bits, there's going to be sequence numbers from 0 to 255, or 256 total sequence numbers. And so this sequence number is going to increment from the first one to the next one to the next one to the next one. And each one of those sequence numbers is going to be associated with a packet. And so you can have a window of up to n consecutive sequence numbers, right? And here is that window here, window size n. So there are n many sequence numbers. Each sequence number is represented as one of these tiny sliver rectangles. And so it's sequential, right? If you start at sequence number 0, the next one's going to sequence number 1, 2, 3, 4, and so forth. And this n doesn't necessarily start at 0. It starts at some point, and then n sequence numbers later, that window ends. And so in that range covered by that n are the set of sequence numbers that are going to be used when the RDT send from above is called, and that sequence number is used to stamp packets. And so the first packet that's sent, the second packet that's sent, they're going to use these sequence numbers from this window going from left to right, because that's how these sequence numbers increment. So these sequence numbers in the schematic, and this is in the book, are color-coded depending on whether or not they're used, whether or not they're in flight, or whether or not they are to be used in the future. So let's take a look at this. So to the left of the sender window, we have these green sequence numbers, and those are the sequence numbers that are already acknowledged. So remember, the sequence number starts at 0, or they could start at 0, and they continually increment. Now, in some examples in the book, they only have sequence numbers that are 4 bits or 3 bits or 2 bits. But in general, sequence numbers are much larger than that. And so you can imagine now, as the sequence number increases, you're going to slide this window, and you're going to now select sequence numbers for the number of concurrent packets that are in flight, meaning you're sending them back to back to back to back to back. Okay? So these green sequence numbers to the left of the window, those are already acknowledged. They've already been used, and we don't care about those right now. So next, we have these yellow sequence numbers. These sequence numbers correspond to packets that have been sent, but no acknowledgement has yet to be received. They're in flight. They're somewhere on the path between the sender and receiver. Okay? And then we have the blue sequence numbers. These are usable but not yet sent, meaning they're available. So if a new call RDT send from above is called from the application, these blue sequence numbers are the next ones that are going to be allocated, stamped on a packet, and then it's going to be sent. And when you call RDT from above and it sends it, that blue turns to yellow. Okay? All right. Now, these other sequence numbers, these kind of white empty bars here, I'll just call them white, colored sliver rectangles, those are sequence numbers that are not usable, right? They're not within that window of size n. Now, of course, what happens when at the left-hand edge of this window, if that now becomes acknowledged, well, that window then moves, right? That's now something that's acknowledged, and you're no longer waiting for it. So this is sometimes called, you'll see this in the literature, it's called a sliding window protocol, right? In the Carosa-Ross book, they call it pipelining, okay? All right, any questions about this? Does that make sense? All right, so we have a bunch of variables. One is called the send base. Now the send base, it marks the beginning sequence number within that window, right? So if the window moves one space, one sequence number to the right, the send base also updates. And so send base is the sequence number that marks the beginning of that sender window of sequence numbers. Then there's also called next sequence num, next seq num. Next sequence num is the next available sequence number. So remember, everything that's yellow has been sent but not yet acknowledged. Anytime you make a new call to send from the application, you have to allocate a sequence number, stamp a packet with it, and then send it through the unreliable channel. Okay, so next sequence number is the next one available. All right, so when you get an acknowledgement, that acknowledgement is going to come with a sequence number. And that acknowledgement is the receiver telling you, the sender, feedback that says, I'm acknowledging to you the fact that I got a packet with this sequence number. And so because this sending of packets stamped with sequence numbers from this window is sequential, these acts are so-called cumulative. So if you have an ACK of the sequence number, that's the second one here, that assumes that the first sequence number at the base was also acknowledged. So anytime you say you receive an acknowledgement with some sequence number, you can assume all the sequence numbers within the window up to and including that sequence number n in the ACK have also been acknowledged. Does that make sense? That's so-called cumulative acknowledgement or cumulative ACKs. Okay, and so the timer associated with the congestion condition is the timer associated with the oldest in-flight packet. What does that mean from the perspective of the window? Here, at the base of the window, we have a yellow bar that represents an unacknowledged or in-flight packet. So the timer is always associated with the base of the window, right? The oldest unacknowledged packet is the one associated with the timer. So in this case, when we get a timeout event, that means the sender can safely assume that something was lost, right? It doesn't know if the ACK was lost or if the packet that was sent was lost. It's going to trigger a resend. And what does it resend? It resends everything that's in flight in the window. So if you had a timer, the timer is associated with the base, and we see all of these yellow sequence numbers are unacknowledged. If the timeout event occurs, even if it was maybe this last packet was the offending packet, it's going to resend every single one sequentially up to and including in the window that's unacknowledged. So what does it do? It'll resend the first yellow one, the second one, third one, and it'll resend all of those yellow sequence numbers up to next sequence num. Okay? Any questions about this? Does that make sense? Okay. And so it's called go back n because it will go back at most with the resending of all n sequence numbers within the window should a timeout event occur. Okay. So let's take a look at the finite state machine for the sender. Now, of course, this is simplified. It's just one state, but there's a lot going on in here. Now, of course, this dotted line connotes the start state. The start state is the only state because it's just one. And we start out with nothing happening. And we have the send base is equal to 1, and the next sequence number is equal to 1. Well, what does that mean? Well, when nothing has been sent, they're all blue. Send base is equal to next sequence number. The next sequence number to be allocated is the send base is, and the send base is at the beginning. It starts at sequence number 1. Okay, so we start out there. This base is 1. Next sequence number is 1. And then RDT send from above is called. So the application, someone calls a send on a socket. And it checks to see if the next sequence number is within the window. What does that mean? Well, it knows that the base starts somewhere, and it's trying to check to see if the next sequence number that's allocated is outside of the bounds of the sender window. Because if if the next sequence number is out here, outside the window, well, you stop. You tell the application, sorry, I can't send that because I've run out of concurrent sequence numbers. Right? I'm only going to allow n packets in flight concurrently. I'm not going to allow n plus 1 packets in flight. So we check to see if it's within the base. If it is, we create a packet with the next sequence number. We add the message data and the checksum inside of that packet. We call unreliable send, UDT send, on that packet that we just created. And you notice here, send packet is now an array, right? So we're going to hold on to an array of n many packets at most. So the burden of storage is now increased because we have a window of size n. we can have n many in-flight packets. Now we need enough buffer space to store n many packets worth of data because we might need to resend them all. So we store that packet we just created, we call UDT send, and then we check to see if the base is the next sequence number. Is this the first packet within that window that we're trying to send? If it is, we start the timer, because remember, the timer is always associated with the oldest unacknowledged sequence number. The oldest unacknowledged sequence number is always the one at the send base at the beginning of our sender window. Does that make sense? Any questions about this? Okay, so we check to see if it's the base. If it is the base, the first one we sent, we start the timer, and then we increment next sequence number. So if next sequence number starts at 1, it's now going to be 2. You call send again, now it's going to be 3. Then it's going to be 4. Then it's going to be 5. And then eventually, the next sequence number is going to be outside of the window, and you refuse the data. You only allow n packets to be concurrently in flight. Okay? All right. So what's the next thing that happens? Well, you get a timeout. And that timeout is associated with the timer, associated with the oldest unacknowledged packet, and that's at the left-hand edge of the sender window. You get a timeout, what do? Well, you restart the timer, start timer, and then you resend everything from the base, the next one, the next one, the next one, up to and including next sequence num -1. So what does that mean? If we go back to the diagram, well, here's next sequence number. That's the next one to be allocated. It has not yet been sent. Everything before it is in flight and unacknowledged. So if we get a timeout, we resend this one, next one, next one, next one, up to next sequence number -1. So we resend all of the unacknowledged in-flight packets within that window. Okay, so we do those UDT sends using those saved copies that we allocated and stored away when we did the original RDT send. So we resend them here. Okay, so then what happens? The other thing that can happen, you have RDT receive, so data comes in from the network layer below. You check the stored checksum against the calculated checksum, and you find it's not corrupt. So then you get the acknowledgement number. What is being acknowledged? And so whatever is being acknowledged, you take that acknowledgement, right, of that received packet, and then you increment it by 1. So you get this ACK, you increment it by 1, and remember, acknowledgements are cumulative. So that means you get something, an acknowledgement, that's going to be the oldest one that you're going to get, right? So here, you'll notice, if you get an ACK, you get the ACK number, and then you check to see if it was the base one. If it was the base one, you're going to stop the timer because you're going to end up shifting that window, all right? Otherwise, you start the timer. And then anything else you get as a sender, it's an ACK, you're just going to ignore it. So you have an RDT receive here on this last self loop, and then you check to see if it's not corrupt, but you don't do anything. You're just throwing away all those ACKs that aren't the ACK that you want. Okay? All right, any questions about this? Make sense? And so I would go through it yourself. You take the finite state machine and you look at the diagram and convince yourself that this actually works. Okay? All right. So that's for the sender. Let's take a look at what happens at the receiver. Now remember, the receiver is getting packets from the sender, and the packets from the sender have sequence numbers, and these sequence numbers have a particular ordering to them, sequence number 1, 2, 3, 4, and so forth. And so we start out, and the sender and receiver are matched. Here, the receiver has a variable called the expected sequence number. What is the sequence number associated with a packet that it's expecting to get? It starts at 1 because here, next sequence number on the sender starts at 1, right? So they're matched together. So we create a packet, an ACK, with sequence number 1, and we save that and we get ready to send that acknowledgement, right? So we create that at time t0, and now we're waiting to get packets from the sender. So now at the receiver, it's expecting sequence number 1, and if it gets sequence number 1, it says, okay, great, I'll deliver that data, and then the next one I'll expect is sequence number 2, and then sequence number 3, and then sequence number 4, and so forth. If it does not get the sequence number associated with the packet that it's expecting, it does not deliver it, does not proceed. It rejects it, right? So let's take a look. So the default behavior, it will always resend that acknowledgement. So it's almost like it's expecting sequence number one. If it got sequence number two, the receiver says, hey, I'm expecting one. If it got three, hey, I'm expecting one. If it got four, hey, I'm expecting one. And that's what this default edge does. The default behavior is to send an acknowledgement describing the sequence number that the receiver is expecting to get. Okay, so now let's take a look at this next edge. RDT receives, so it gets the packet from below. It checks the stored checksum against a calculated checksum to see if it's corrupt. And if it's not corrupt, now it checks the sequence number in the received packet against what it's expecting. If it got what it's expecting, it extracts the data, then it delivers the data to the application above, and then it creates an acknowledgement, and then it does the UDT send for that ACK, and then increments the expected sequence number. So if it gets what it's expecting, it acknowledges it with the UDT send of that ACK, and then increments the next expected sequence number. So now it's waiting for sequence number 2. Okay? And so in every case, the receiver, it will ACK whatever it's expecting, and then when it gets what it's expecting, it'll deliver it, and then increment that sequence number to expect the next sequence number. Okay? Right, any questions about this? Does that make sense? Okay. So it's ACK only. It only sends an acknowledgement for a correctly received packet with the highest in-order sequence number. So things that are out of order, it throws them away. It only accepts and delivers things that are in order based on the sequence number, and it's that next expected sequence number is what it uses to trigger that. So it only has to remember one piece of information, that's expected sequence number. And the sender and receiver endpoints in the transport layer runtime are synchronized with one another. They both start at 1. Okay? All right. Any questions? No? All right. So here's an example protocol diagram for go back and in action. And so on the left-hand column here, we have the window of sequence numbers. And typically when this is depicted, you're going to have a bunch of integers, right? And those integers may cycle depending on the number of bits in the representation of the sequence number. And you're going to see the window represented as a box. In this case, it's a blue shaded box. And the sequence numbers inside of that box are the sequence numbers in that sender window. So in this particular case, we see in the initial time, our window is of size n equals 4. So you can have 4 sequence numbers in this window that are covered. And in its initial configuration, we see sequence numbers 0, 1, 2, and 3 are available for the sender. Okay? And so we also have the sender behavior here in this next column, and every edge represents a packet that's sent from the sender to receiver. And then likewise, we have the receiver. It's going to get something, a packet, and then send an ACK back across the wire as feedback to the sender. And those ACKs are the green arrows. Okay, so let's take a look. I'm going to go over to my laptop here so I can use the arrow. So here in the beginning, we have the initial configuration, sequence number 0, 1, 2, and 3. So what does it do? It sends up to 4 packets back to back to back that can be unacknowledged. And so it sends packets 0, 1, 2, and 3, and then it waits. Why does it wait? Because once you send 0, 1, 2, and 3, you've now used up all those sequence numbers in the window. And if you come again and call RDT send, it's going to say stop, blocked. You cannot send anymore because I've reached the limit. I've reached n equals 4 packets that are in flight. So now packet 0 comes across, packet 1 comes across. So 0 comes across the receiver, it gets 0, sends back ACK 0. It gets 1, okay, great, sends back ACK 1 across the wire. Now packet 2, let's assume that gets dropped. It hits a router on the path in between the sender and receiver, it gets dropped because it meets a full router buffer. And then packet 3 gets sent, and packet 3 makes its way through. So from the perspective of the receiver, it got 0, ACKed it. It got 1, ACKed it. It didn't get 2, but it got 3. So it got packet 3, but at that point, the next expected sequence number is 2. So what did it do? It was expecting, the receiver was expecting packet 2. It got packet 3, so it discarded it, just ignored it. and it sent an ACK of 1 to tell it, you gave me 3, the last ACK I sent was 1, so I'm going to resend that ACK. Okay, so now, in the meantime, when packet 1's ACK was received, what did the sender do? Well, it updated the window because now the base of the window was acknowledged, so it slides the window, right? Updates the window. When it updated the window, now it covers sequence numbers 1, 2, 3, and now 4, right? Now 1, 2, and 3, those are in flight, right? 4 is the new sequence number. So because 4 is a new sequence number, the sender now can send packet 4. Okay, so the ACK for 0 comes in, ACK for 1 comes in, and the sender slides that window in response to the ACK of 0 and in response to the ACK of 1. So now 4 and 5 are available to be sent. So what does it do? It accepts packets, RDT sends from above, and sends packet 4 and packet 5. Okay, so now packet 4 and 5 are in flight, and on the receiver, it gets packet 4, but it hasn't yet gotten packet 2, right? When it got packet 3 out of order, meaning that it was expecting 2, it got 3, it sent ACK 1. Now when it gets 4, it discards it because it's not what it's expecting, right? It discards it and sends ACK 1. It gets packet 5, it discards it as well and sends ACK 1. So the receiver is throwing away everything that it got because it did not get packet 2, right? Okay, so now after doing all this throwaway of packet 3, 4, and 5 on the receiver side, eventually that timeout expires. Now at that point, this window has slid to the right 2 positions, revealing 4 and 5, and it sent 4 and 5, but it has not moved past 2. And the reason why the left-hand edge of that sender window has not moved past 2, because 2 is unacknowledged. Because remember, 2 was lost. And so the ACK has not been received for packet number 2. So the timeout expires, and that timeout is associated with the oldest unacknowledged, excuse me, losing my voice. Excuse me. And so that timer is associated with the oldest unacknowledged packet, and that just happens to be packet with sequence number 2. So what does it do? It resends every packet in the window. The timer expires, and it resends 2, 3, 4, and 5. Okay, so packet 2, 3, 4, and 5 come across the wire. From the receiver side, now finally it's received packet 2. It delivers it to the application above, sends ACK 2. It receives packet 3. It's in order. It delivers it, sends the ACK for 3. It receives 4, delivers it, sends ACK for 4, and the same thing for packet 5, delivers and sends the ACK for it, because they're all now in order. Okay. Any questions about this? Does that make sense? And so the interplay between the sender and the receiver only sends the acknowledgement for what it has successfully received. And if what it receives as a packet from the sender in the future is out of order, it discards it and resends the acknowledgement. Okay? All right. Now, in response on the sender to getting the acknowledgement, it shifts that window if that acknowledgement is for the oldest unacknowledged packet in the window, because everything has to be done sequentially from the oldest up to the newest, or the smallest sequence number up to the largest sequence number. Okay. So let's take a look at selective repeat. At the outset, I said selective repeat has individual timers. Rather than sending all the packets within the window or resending all the packets within the window that are unacknowledged, it can send individual packets or resend individual packets. But the burden here from a design standpoint is needing more timers. You need a timer for every single packet. And so in selective repeat, the receiver individually acknowledges all correctly received packets. And so it buffers these packets, and it buffers them because now it can receive things out of order, and it only delivers things that are received in order, right? So there's a savings in terms of the amount of traffic that's resent over the wire, but the other burden from an engineering standpoint or cost is that you need more buffering on the receiver side, right? All right, so the sender only resends packets on an individual basis for which the acknowledgement has not yet been received. And the sender window can send n consecutive sequence numbers, right? Again, the sender has to have a buffer for each of these n many packets because it might need to resend. Okay? All right, any questions about this? All right. So this is what selective repeat looks like. It's a little bit more complex. Again, we have a set of sequence numbers. That's each of these these little bars, and they're color coded. Things that are white are not usable. And we see that if we're outside of the sender window, the sender's up above and the receiver's down below. If we're outside of the bounds of the size n sender window, it's colored white because those sequence numbers are not used. Now, a yellow sequence number has been sent but not yet acknowledged. And you notice here there are gaps, right? Some are sent, not yet acknowledged, and some are acknowledged. Now, if you're acknowledging individual packets and you have individual timers to resend on a per packet basis, you're going to have gaps. And we have the green here are acknowledged, the yellow are in flight but unacknowledged, and the blue, as before, are usable and not yet sent. So here we have next sequence number, and as we call RDT send from above, this next sequence number is going to allocate to as a sequence number for a packet, and then it's going to move one to the right by incrementing. Okay? So then, as you get acknowledgments, this window will not move to the right until those packets at the base are acknowledged, or they turn green in this case, right? Okay. Any questions about this? That make sense? Okay. So let's take a look at the receiver side. On the receiver side, we have a buffer, and this buffer is going to store up to n packets, and it's going to deliver packets in order. Because these things are resent on an individual basis using timers, you're going to have some gaps here. So here in this window, the blue sequence numbers are acceptable. They're within the window, so they can come in the future. The purple here, is that purple or pink? It looks like pink. I'll just call it pink. The pink ones are buffered. They already have been acknowledged, but they're out of order. And remember, when you send data, you're sending it one sequence number at a time. The first sequence number, second, third, fourth, fifth, sixth, etc. And so you can have gaps here in the receiver window. These gray sequence numbers are expected but not yet received. And so when you're going to deliver data, you deliver data to the application layer above in order. And so in this particular case, you're not going to deliver these purple sequence numbers, which have been acknowledged and received. You're going to deliver them only once you've delivered everything to the left. And so you deliver things from left to right across the window in terms of the sequence numbers. Okay? And so over time, what will happen is these gaps get filled in as those timers, individual timers expire and the sender resends them. And then once they're filled in sequence, that's when you deliver them and you stop when you hit a gap. Okay? All right. Any questions about this? So again, like the case of go back n, please review it yourself and convince yourself that it works. Okay, so let's take a look at the behavior of selective repeat. And I don't believe there's a finite state machine in the book for it. They just have a description of the data. And so on the sender side, when you get data from above, you look at the next available sequence number within the window, you create a packet, and then you send it. So what does that mean? Here, next sequence number, that's blue. So it gets allocated, and next sequence number is then going to increment, and that blue sequence number is going to change from blue to yellow, right? And it doesn't change to green until the acknowledgement for it has come in. Okay, so we allocate the next available sequence number, and then a packet we allocate, and then we send it. That's the sender. And then if you get a timeout, that timeout is per packet. It's per individual sequence number. So if you get a timeout for the nth sequence number, it resends only that nth packet. It doesn't resend everything in the window, right? This is selective repeat. Now, if you get an acknowledgement, that acknowledgement is for a particular packet. So if you get a timeout, you resend. If you get an acknowledgement, you check to see if it's in the window, and then you mark that single packet as being received. So selective repeat does not have cumulative acts. So I'll say that again. Selective repeat does not have cumulative acts. It's individual packet acts in selective repeat. So if you get an acknowledgement for a particular packet with sequence number n, you check to see if it's within the window, and then you mark it as being received. So what does that mean? If you get an ACK, you can only get ACKs for yellow sequence numbers. If you get an ACK for yellow sequence number, it now changes to green. Okay? All right. Any questions about this? So then you advance the window base to the oldest unacknowledged packet that has recently been acknowledged. And what do I mean by that? So here we have two in-flight unacknowledged packets that are oldest in the send window. We don't move the base for the send window. If this last one, the oldest one, the first one in the sender window, that's the oldest unacknowledged packet. If that changes to green, then we shift the sender window, right? So we only shift the sender window associated with the oldest packet suddenly being acknowledged, turning to green. Okay. All right, so let's take a look at the receiver. So the receiver gets packets from the sender, and those packets it gets from the sender have sequence numbers. And these sequence numbers, if the sequence number it gets for a packet is within the receiver window, it sends the acknowledgement for that single packet. And remember, for selective repeat, when the receiver sends an ACK, it is an individual ACK, not a cumulative ACK. That's really important to remember. And so you send an ACK for that packet. Now, if that packet stamped with sequence number n, if it's out of order, meaning it's not the oldest in the receiver window, then you buffer it, you store it, because you're not going to deliver it until you have every sequence number in the window before it. So if it's out of order, you buffer it. If it's in order, you deliver everything in the buffer in order until you get to the first gap, right? So that window in the receiver window, here we have an expected but not yet received packet as the oldest packet in the window on the receiver. And here, the two next to it, those have been received and buffered and acknowledged. So the moment we get this oldest one, once it arrives, it turns to purple, and then we shift the receiver window and we deliver this newly purple gray one, the next one, and the next one, and then we stop, right? And so when you deliver packets, you deliver them in order from the receiver buffer. Okay. Any questions about this? Okay, does that make sense? All right, so again, please go through this material in the book and try it yourself and look at the diagram and convince yourself that it works. It does work. Okay, so let me check the time. 12:49. So let's take a look at selective repeat in action. Now again, selective repeat had individual ACKs for a packet, okay, and individual delivery once they're in order. Same scenario, we have a window of size 4, so n equals 4, and this blue window here covers sequence numbers in the beginning, 0, 1, 2, and 3. And so we start out, we have 4 packets that can be in flight. So we send packet 0, packet 1, packet 2, and packet 3. And now any call RDT send from above, it blocks, it waits, because we've now exhausted the number of packets that can be in flight in the pipeline protocol. So packet 0, let's say it arrives at the receiver. It receives packet 0, it sends ACK for 0. It receives packet 1, sends the ACK for 1. It doesn't get packet 2. Let's say packet 2 was lost. It receives packet 3, and now packet 3, it's out of order. Because the last thing that the receiver got was packet 1, it's expecting to get packet 2 next. Packet 2 is missing. So because it got packet 3, it buffers it and sends back an ACK for 3. Now remember, these are individualized ACKs. So now we have a gap. What's missing from the receiver is packet 2, right? So packet 0, 1, and 3, those are purple in the receiver window, and the space for packet 2 in the receiver window is gray, going by that diagram from previously. So now what happens? Okay, well, the ACK for 1 arrives at the sender, so it slides the window 1 space, and so now the window's over sequence numbers 1, 2, 3, 4. The ACK for 1 comes in, so we get the ACK for 0, ACK for 1, and this window on the sender side, it moves 2 spaces. So now we have sequence number 2, 3, 4, and 5. 4 and 5 are now new, so the sender is now free to send packets 4 and 5. Now, you'll notice this window does not move past packet 2 because it has not yet gotten the ACK for packet 2. So it will never slide that window because 2 has been unacknowledged, right? Okay, so now what happens? So packet 4 and 5 arrive. Packet 3 was buffered. It sent ACK3. Packet 4 arrived. Well, it was expecting packet 2, but it got 4. It's out of order, so it buffers it and sends the ACK for 4. Packet 5 arrived. It was buffered, and it sent the ACK for 5. And so from the perspective of the receiver, well, it got 3, it was out of order, it buffered it. Got 4 is out of order, it buffered it. It got 5, and it buffered it because those are all out of order. It was expecting to get packet 2, which was lost. So now what happens, packet 3, 4, and 5 are buffered, and now packet 2's timer times out. It fires, right? And that's an individual packet timer. So what does the sender do? It resends packet 2. So it resends packet 2. And let's see what happens here. So packet 2 arrives at the receiver, and previously it buffered 3, 4, and 5. So now 2 has been received. It sends the ACK for 2, and it now has 2, 3, 4, and 5. So what does it do? It delivers 2, 3, 4, and 5 at the receiver side because now all of those are in order, meaning that there are no gaps in the sequence numbers associated with received packets. Okay, any questions about this? Does that make sense? Bless you. All right. So there's a little bit of an issue with selective repeat. There's some ambiguity here. And the ambiguity has to do with the relationship between the size of the window and the cycle time, as it were, of the sequence numbers. In this particular example, the window size is size 3. And you'll notice here the sequence numbers, it starts at 0, goes 0, 1, 2, 3, so it's a 2-bit sequence number. So it goes 0, 1, 2, 3, and then starts back at 0 again, right? And the cycle time tells you when you have a certain representation for a sequence number, it increments when you get to the next sequence number, but what happens when you have all 1 bits? You start back at 0 again, right? So we see that the sequence number starts back after 4 different numbers by incrementing, and the window is of size 3. It covers more than half of the sequence numbers. So this introduces a little bit of an ambiguity, right? And we'll talk about that ambiguity. So here we have the sender and receiver, and we have in the initial position on the sender side, the sender window covers sequence numbers 0, 1, and 2. So it sends packet 0, 1, and 2. Okay. Now the receiver, it gets packet 0, delivers it, sends back the ACK for 0. It gets packet 1, delivers it, sends back the ACK for 1. And you'll notice when 0 and 1's ACK are received, the window on the sender side, it slides because the oldest unacknowledged packet is acknowledged, right? And so now, after the ACK for packet 1 is received back at the sender, our sender window is covering 2, 3, and 0. So let's say when it sent 0, 1, 2, and 3, packet 3 was lost. It hit a router, and the router was congested, and it ended up dropping packet 3. So what happens here? Remember, this is selective repeat. In the meantime, well, packet 0 and 1 were received in order at the receiver. And so the receiver window also updates. And you'll see here, when 0 was received, it slid the receiver window. When packet 1 was received, it slid the receiver window, again, one more space to the right. And now it's allowing you to reuse sequence number 0, right? And so let's see what happens here. So packet 3 was lost, and we've updated the window, and now it sends packet 0 here. Now, what ends up happening is that it's going to accept packet number 0 with sequence number 0, right? Okay, that seems fine, and eventually packet 3 will get resent, but there's some ambiguity between this scenario and this next scenario. Okay, so let's see what happens in the second scenario. So packet 0, same deal. The window starts covering sequence numbers 0, 1, and 2, and we send packet 0, 1, and 2. Okay, so let's say 0, 1, and 2 are received by the receiver, and each time it receives a packet, it delivers it, sends an ACK, and slides the window. So that means it delivers it, sends an ACK, slides the window, delivers, sends an ACK, slides the window, delivers, sends an ACK, slides the window. So now we see on the receiver side, the window is covering sequence numbers 3, 0, and 1. Those are 3 new sequence numbers that have recycled that are now expected by the receiver. But these acts have been lost on the reverse path going back to the sender. Now, of course, what does the sender do if it doesn't get an ACK for packet 0? Well, that timeout on an individual packet basis, it fires and it resends packet 0. Now, it resends packet 0, that's a resend, but on the receiver side, you'll notice here, because 0 is an expected sequence number, right, because it got it previously and shifted the window, it takes that resend, that retransmission, as if it were a brand new packet. So what does that mean in real terms? It means that if you're watching a video, all of a sudden you see a frame again that you just saw, right? And the problem is that the receiver doesn't know what's happening in the sender. All it sees is the sequence number associated with the packets that it's getting. And the problem from this stems from the relationship between the window size and the cycle time of the sequence number. And so the cycle time of the sequence number should be more than twice the window size, right? If the window size were half, this wouldn't happen. And so what does this mean in practical terms? Well, if you're tinkering with operating system kernels and you're tinkering with the parameters of your window protocol for a TCP runtime and operating system, and you want to choose a sequence number size and a window size, you want to make sure the window size is less than half of the sequence number cycle time, okay? All right, or else you have ambiguity, and that will manifest itself in retransmissions being taken as if they were new data, okay? All right, any questions about this? All right, okay. So the receiver doesn't see any difference between these two, and you really have to be careful with how you set the window size if you're controlling. Now, this doesn't really affect you too much in something like a desktop or a laptop, but if you're dealing with small mobile devices, this might affect you. The sequence number space is pretty big for TCP on a desktop. Okay. All right. Any questions about that? No questions? No? All right. So let's take a look at TCP. We've talked more generally about pipeline protocols as an extension of reliable data transport, and we've talked about RDT 1.0, RDT 2.0, 2.1, 2.2, RDT 3.0 added timers to handle packet loss and congestion. And then we talked about pipelining to increase the utilization of our connection between the sender and receiver endpoint. So now we're going to take a look at the specific design decisions that were taken by TCP, Transmission Control Protocol. Before this point, we're talking more generally about reliable data transport that does pipelining. And the two major ways of doing pipelining are selective repeat and go back in, where go back in resends the entire window's worth of packets using cumulative acts, where selective repeat has a per packet individual acknowledgement using individual timers. Okay, so what is TCP? Now, there are a bunch of RFCs. You're welcome to Google search them and read them with all the details about the TCP standard specifications. It's point-to-point, so you have one sender and one receiver. This is in contrast to something called multicast. Multicast is an entirely different thing. TCP does not do multicast. There is IP multicast available. It does reliable in-order byte stream delivery. And so when we talked about sequence numbers, TCP treats sequence numbers as indices into a stream of virtual bytes, right? And that stream of virtual bytes is effectively chopped up into units, where those units are the amount of payload that will fit inside of a single TCP segment. And so we have reliable in-order byte streams. There's no message boundaries. It's pipelined, so we have sender and receiver windows. And TCP congestion control and flow control, which we'll talk about as part of this module, set the window size. And so we talked about a window of size n. In TCP, based on congestion and flow, it'll actually adjust the size of the window of the sender, right? And we'll talk about that as well. It's full duplex, meaning that it's bidirectional. And so we've only been talking about one direction from the sender to receiver. But if we have two communicating endpoints, there's a perspective where one endpoint is the sender and the other is the receiver, and then there's another perspective where one endpoint is the receiver and the other is the sender. So if you have a client talking to a server, when we talk about the basic protocol, we talk about sender and receiver, but from the TCP standpoint, the client is both a sender and a receiver, and the server is both a sender and a receiver, those behaviors. So when we look at the endpoints for a client and a server inside of TCP, there's a sender buffer and a receiver buffer in the client. There's a sender buffer and a receiver buffer in the server, right? And so this is the relationship between the socket and the transport layer. And this particular segment, we're talking about the design choices for TCP specifically, okay? All right, so it's full duplex. That means you have bidirectional data flow in the same connection. And there's a quantity called MSS, maximum segment size. And that MSS talks about the payload that a TCP segment can accept. It's connection oriented, so that means that there's a handshaking protocol. And when you create a socket in the beginning, there's an exchange of messages between the initiator and the client and the server endpoint. And this is to establish resources needed. Now, these resources include timers, they include buffers, and as well as the runtime implementation, an instance of that running to walk through the implementation of these finite state machines for the protocol. And so this connection-oriented part, as part of TCP, is the so-called three-way handshake, which is used for the initiator to ask the server, can you establish these resources needed, yes or no? Okay. It's also flow controlled, and the flow controlling is the receiver giving information back to the sender corresponding to how much empty buffer space it has so that the sender will not overwhelm the receiver with data. Okay. So let's take a look at the TCP segment structure. And so we said from before there are port numbers. We have the source port number and the destination port number. Each one of those port numbers is 16 bits long. And so you have 2 to the 16 or 65535 different port numbers you can set for the source and destination. We also have a 32-bit sequence number, right? That's a lot of cycle time, right? So 2 to the 32 is the sequence number. And in TCP, the sequence number represents a position into a stream of bytes, right? So you have the sequence number and you also have an acknowledgement number, right? And the acknowledgement is also 32 bits long. Okay, we have a bunch of flags, and these flags do things like allow you to establish connections. And that's the reset, synchronization, and the finish bits. And so these bits are set as part of handshaking, the RS and F bits. And then we have some other stuff like the ACK bit is set, or flag is set, to connote that the particular segment is an acknowledgement versus a data carrying segment. Okay, we also have the checksum, and the checksum is just like the checksum we talked about for UDP. It's calculated using 2's complement arithmetic and using carry out, and it's used to store this checksum value, and it's compared against a calculated checksum to see if there's corruption in this. And then we have some options, and then down below the payload information, that's the application data. So if this were an HTTP GET request from a browser, the HTTP GET request would be in this application data section, and that's payload for the transport layer. So everything above this application data is transport layer header information. And this is for specifically for TCP for the segment structure. Okay, all right. Any questions about this? Does that make sense? All right, so let's take a look, it's 105, at sequence numbers. Now, in TCP, a sequence number is represented as a virtual stream of bytes. There's no eraser. Let me see. I'll tell you what, I'll go on the other side. So let's say you have some image data, and let's say that's the first image. And that image, let's assume that that image takes 4 packets to store it, right? So you have these 4 packets, and here's the header information, and here's the payload down below. So that's packet 1. We have packet 2. There's the header. Packet 3. So header 1, header 2, here's header 3, and here's header 4. Now, when you're trying to send data, this data you can think of as being one long strip of data, one row at a time, right? So you can actually take this image and you can treat this image like a big long tape of bytes, right? So you could take strips of this image data, right, and concatenate them with one another and treat them like one big long continuous strip of bytes. Now, of course, let's say for this big long strip of bytes, you have this first part, you divide into 4 pieces, for example, 2, 3, 4. And the first piece you're going to put here in the first TCP segment. The second piece you're going to put in the second piece you're going to put in the second TCP segment. The third piece you're going to put in the third TCP segment. And the fourth piece of that strip of bytes are you going to put in the fourth segment. Now, when you look at sequence numbers in TCP, well, the sequence number in TCP is not treated as packet 0, packet 1, packet 2. It's treated as what is the offset associated with that data for that contiguous sequence of bits, right? So here, let's say that sequence, this was position 0. So the sequence number here would be 0. And let's say this sequence number, that was position 1024, right, in that contiguous strip. Well, the sequence number here would be 1024. And let's say if this sequence number here was 2048, the sequence number spec here would be 2048. So what sequence numbers represent in TCP is the offset into the continuous stream of bits represented by what is stored in the payload area for that segment. Does that make sense? Okay. So a byte stream offset is what TCP uses as a sequence number, right? And so the sequence number of the next expected byte is what is acknowledged. And in TCP, these acknowledgements are cumulative. Why are they cumulative? Because if you get successfully the byte that's over here, that means all the bytes before it have been received because it assumes it's sequential. Okay? All right. So let's take a look. Acknowledgements use a sequence number of the next byte expected from the other side, acts are cumulative, and there's no real standard in TCP for how out-of-order segments are handled. You could either buffer them and deliver them, or you could just throw them away and get them whenever the timeout expires. So here we have the window on the sender side for TCP, and we have the sender sequence number space. And remember, these are offsets for bytes. And so the next sequence number represents the next offset in the bytes. And so whenever the receiver in TCP gets a segment of information, it asks how many bytes are inside of this. My next sequence number is going to be whatever my previous sequence number is, plus the amount of bytes that's in the payload area for the received segment. Okay? All right. Any questions? All right. So here we have an outgoing segment from a sender, and the sequence number, next sequence number here is from this usable but not yet sent part of the number space for the window on the sender buffer. And then here we have incoming segment and acknowledgement. And the acknowledgement would say, okay, well, the acknowledgement bit is set, so we know it's an ACK segment. And then the sequence number, the ACK number, represents the offset in that sequence that was received. So here we have this virtual stream of bytes. The sequence number for the sender represents where in that byte stream corresponds to data in the payload area of that segment. And then on the receiver side, what it's received, it has the ACK number. The ACK number represents a position in that sequence as well. Okay, so here's an example, and this is more realistic for what happens in real life. And we have two communicating endpoints, and we'll end with this, host A and host B. and host A is only going to send a single character to host B, and a single character in ASCII is 1 byte, 8 bits. And so here we have sequence number 42 that host A is going to send. It sends the character C to host B. And on the reverse path, you'll notice here it's bidirectional. So not only is it sending sequence number for the data that it wants to send to host B, it's also sending an acknowledgement to host B for what host B sent back to it the last time. So here on the forward path from A to B, we have sequence number 42. The data is C and the acknowledgement is 79. So host B rather, receives this and it says, okay, you gave me sequence number 42 for the data C. I'm going to send an acknowledgement on the reverse path for 43 because it says I successfully received that piece of data at position 42 in the stream. So the next piece of data I'm going to expect is going to be the data at position 43. So that's what that ACK means. So then the receiver, it maybe is going to echo, it's going to send back what it receives. So it sends back an A, and the sequence number is 79. So sequence number 79, right? And it's acknowledging 43, the next thing it's expecting from A. It gets that C character, and its sequence number for what it's sending is 43, and then the ACK is 80, right? And so you notice every time you ACK, it's one more than what was sent the last time, okay? Does that make sense? Okay, so it is 1:13. We'll end there, and we'll pick back up with this on Thursday. I will see you all on Thursday.